Junting is visiting Pavesh, and we have enlisted him on a last-minute call to tell us about this result that I already heard the preview of. Thanks.
Okay, thank you so much for the introduction, and of course, thanks for giving me this opportunity. Today I'll be talking about rounding large independent sets in expanders. This is joint work with Mitali Bhavna, who is at MIT, and Pravesh, who is right here. Okay, I'll jump right in. So in this work, we study the problem of finding large independent sets in a graph. This is probably the most fundamental problem in computer science and has been studied for many decades. So one of the most famous results is that it is NP hard to find the maximum clique or independent set in a graph. But we know something much stronger. We know a stronger hardness of approximation result for this problem. Specifically, if you're given a graph that contains a 1/n polylog independent set, then it is NP hard to find an n to the -1 plus little of 1 size independent set. This is following works on the PCP theorem. And for this talk, I will always use fractional size. So whenever I say an independent set of size epsilon, I mean that the set contains an epsilon fraction of the vertices. Okay, so this is a very strong hardness result, and notice that n to the -1 without the little o of 1 is just a single vertex. So this says that we cannot do much better than just outputting a single vertex. What about algorithms? Well, the best known algorithm so far is that given a graph with 1/n polylog size independent set, it outputs a log square over n divided by n size set. And this is done by Feiger in 2004. This is the best known algorithm so far. We don't know anything better than this. Okay, so basically it's hard to do anything in this regime. This is the best known, and we don't know anything better within the last 20 years. But notice that these results are all in the low completeness regime. So here we only guarantee that the graph contains a sub-constant size independent set. So what about the high completeness case? What if the graph has a larger independent set? So here we study the case when the graph contains an independent set of size constant. So it has a large independent set, constant size. So we can expect that maybe there's a better algorithm that finds a large independent set, given such a large independent set in the graph. Okay, there's a trivial algorithm for this case. When the graph contains an independent set of size larger than half plus epsilon, then we can find one that is 2 epsilon. And this is a standard factor 2 approximation algorithm for vertex cover. And you can see this by noting that the complement of an independent set is a vertex cover. So if we have a 2 approximation algorithm for vertex cover, then we get this result for independent set. Okay, so this is the trivial baseline. We can do slightly better. Karakostas proved that if you're given a graph with half minus 1/√log n size independent set, then you can find a 1/√log n size set. And this is building on the work of the famous work by Aurora Rao and Vazirani, who proved a root log n approximation for sparsely cut. So this is roughly where this root log n comes from. And this is the best known algorithm so far. For example, if we change this to half minus epsilon for any constant epsilon, and we know nothing better. We know nothing better than the algorithm by Feiger in 2004. On the hardness side, assuming the unique games conjecture, and for any constant epsilon, we cannot find an epsilon size independent set. So it's also a pretty strong hardness result, assuming the unique games conjecture. And but this hardness result does not rule out the possibility of finding an n to the negative epsilon size independent set in polynomial time. So even assuming some stronger variant of the unique games conjecture, some variant regarding like stronger completeness and soundness, this is not ruled out. This is possible. Of course, this is open. We don't know anything better than this algorithm. right now. So at this point, you might be asking, why do people study the high completeness case? It turns out that is because of a strong connection to coloring 3 colorable graphs. Note that any 3 colorable graph contains a 1/3 size independent set. This is just because each color class forms an independent set. So the graph is partitioned into 3 of these independent sets. One of them must be at least 1/3 size. Well, there's a long line of work studying coloring 3 colorable graphs with as few colors as possible. And this line of work started from the famous work by Avi, who gave root n, who showed that you can color 3 colorable graphs using root n colors. The best known right now is using n to the 0.2 colors, roughly, or slightly smaller than 0.2. And let me mention that all these works, they focus on finding large independent sets in a 3 colorable graph. Because intuitively, if you're able to find a large independent set, then you can color that set with 1 color, remove them, and then repeat on the remaining graph. So if you can find a large enough independent set, then it automatically says that you can find color the graph with few colors. And this is the best known result right now. So Kawarabayashi and Thorup showed that you're able to find an n to the negative 0.199 size independent set in a 3 colorable graph. Okay, and again, there's hardness result for this. It's hard to find any constant size independent set. Here, there's an asterisk here because it's assuming some variant of the unique games conjecture that requires perfect completeness. But for this talk, I won't go into details about this. And another thing I want to mention is that starting from Carnegie and Motwani in Sudan and a lot of the other works, later works, the algorithm solve the SDP relaxation and then design a rounding algorithm to find a large independent set. Oh, yes.
So as far as we know, you might be able to color with log n colors, a 3 colorable graph.
Yeah.
That is not ruled out, yes. Yeah, but that is pretty hard. Yes, okay, so all these later algorithms, they rely on rounding SDP relaxations. So one can view this like lack of progress, like this is kind of polynomial colors is quite large. The lack of progress, we can view this as maybe a lack of rounding algorithm. So this is one main motivation of our work, is to study different or better techniques to round SDP relaxation. Okay, but anyway, as far as we can tell, this problem is super hard for the worst case, for worst case graphs. So I guess, so now the natural question is, can we do better if we have more assumptions on the graph? Yeah, like are there any non-trivial algorithms if you assume additional structure, additional assumptions on the input graph? And people started with k-colorable random graphs. This is a model where you sample a random graph, let's say a GNP, and then you partition the graph into k clusters and then remove the edges within the clusters. Then clearly this becomes a k-colorable graph. This started with the work of Blum and Spencer, and later by Alon and Kahale. They observed that the bottom eigenvectors of the adjacency matrix contains information about the color classes. So when you do some kind of spectral clustering using these eigenvectors, you can recover the k color classes. And this idea has been extended to planted k coloring on two-sided expanders. So two-sided expanders means that the maximum between lambda2, this is the over of the adjacency matrix, and the minimum eigenvalue, this is the magnitude of the negative eigenvalues, is bounded by above. Then similar technique, which we call the bottom eigenspace enumeration, is able to recover the color classes. So this is basically the same idea as this work. And the high-level intuition is that suppose you start with a two-sided expander where you don't have any large negative eigenvalues, and then now you plant a k coloring by partitioning and then removing the edges within clusters. You're going to introduce new large negative eigenvalues. But because the original graph has no large negative eigenvalues, these new ones and their corresponding eigenvectors contain a lot of information about the color classes. So this is a rough idea of bottom eigenspace enumeration. And notice.
What do they get?
Hmm?
What do they get? They find their k color.
Yeah, so they're able to recover the k colors like almost exactly. Yes. But notice that the idea that I just told you has nothing to do with lambda 2. All they need is that the minimum eigenvalues of this graph has bounded magnitude. So they only care about the negative eigenvalues.
So I thought like for expanders, they can recover a large independent set, but they usually can't find a coloring.
Yeah, so there are some, they can find an almost coloring, but for exact coloring, they actually show some hardness result, even if they assume a random graph. But if you only care about finding an almost k coloring or yeah, or if you only care about a large independent set, then they're able to do this. Okay, so I guess the natural question here is what about one-sided expanders? So one-sided expander just means that we only have guarantees on the second eigenvalue of the adjacency matrix, which is equivalently the spectral gap, lambda, defined as 1 minus the second eigenvalue, is at least 1 minus epsilon. So from now on, I'm going to use lambda to denote the spectral gap instead of the eigenvalues of the adjacency matrix. Sorry, sorry for the confusion, if there's any. Okay. And so this is the usual notion of an expander, because a large spectral gap is closely connected to edge expansion. So when people generally say an edge expander, usually mean it in a combinatorial way, which means that it has large spectral gap. And in particular, we don't really have any guarantees on the negative eigenvalues of the adjacency matrix. So let me tell you a hardness result first. We show that for any constant epsilon, if the graph is almost four colorable, but has a super strong expansion, this is lambda is larger than 1 minus little o of 1, then it's still usually hard to find an independent set of constant size. Here, almost four colorable means that you can remove a tiny fraction of vertices, and the resulting graph is four colorable. Okay.
But wait, a Ramanujan graph will have 1 minus 1 over d, right?
Ramanujan, yes.
So but anyway, you are not looking at constant. The degree in your graph will be large.
Yes. Yeah.
Why is the problem?
Yeah, exactly.
Yeah. Okay. Yeah. If it's too dense or too sparse, then it's easy. So somewhere in the middle is hard. Okay. And I'll quickly show you the proof. It's very simple, like one line. So the reduction starts from the result by Benso and Colt. They show that given a graph, it is usually hard to distinguish between a graph that has two disjoint independent sets of size half minus epsilon. This equivalently means that is epsilon almost two colorable, so almost bipartite graph. It's hard to distinguish between this case and this case, where the graph has no independent set of size epsilon. So now what do we do? So let's say we're given a graph, and we just add a large, dense, expanding bipartite graph. Let's look at the completeness case. Suppose the graph has two disjoint independent sets, so it's epsilon almost two colorable. Then adding this, because the bipartite graph is two colorable, the resulting graph is almost four colorable. The soundness case, if it has no independent set of size epsilon, then adding edges cannot increase any the maximum independent set size. Okay, and because we can assume that the original graph is like not too dense, adding a dense bipartite graph, and let's assume that it's also expanding, will blow up the spectral gap. It's gonna have spectral gap close to 1. That's it. That's the entire proof of this hardness result. Are there any questions about this? Okay, and just want to mention that this reduction must have create many negative eigenvalues. Otherwise, if there are only a few negative eigenvalues, then the previous technique using bottom eigenspace enumeration can likely find some constant size independent set, which would contradict unique games conjecture. Okay. So now I will talk about our results. Our result says that if you change this 4 to 3, then you get an algorithm, surprisingly. Here's a statement. Given an almost 3-colorable graph with spectral gap, at least 1 minus some small constant, then there's an algorithm that finds a constant size independent set. Just as a comparison, I'll copy the previous hardness result. We change 3 to 4. Then even if the spectral gap is at least 1 minus root of 1, it's usually hard to find a large independent set. Okay, so this is quite surprising to us when we first realized this. There seems to be some fundamental difference between 3 and 4 colorable graphs. And to be honest, I don't think we fully understand this. But towards the end, if I have time, I'll tell you a bit about why the proof fails to generalize to 4 colorable graphs.
Actually, can you say anything about an algorithm for finding a coloring using few colors? Because it seems like if you find independent set in field, then you might like destroy the expansion.
Yes, exactly. Exactly. That is exactly the issue. So if when you recurse, you might destroy the expansion. Yeah, and actually, this is something I'll talk about towards the end about some open directions.
Although the rounding might give you many sets that you don't have. It's not clear what you find in this theorem, but maybe you can find not just one, but many independent sets, and not recurse in the trivial way, but rather have I don't know, maybe most of the graph.
I see. Yeah, that's an interesting question. Our algorithm only finds one. We don't find many of them, but
There is no randomness in the rounding.
no, the
Okay.
algorithm. There is some randomness, but I think we don't guarantee many.
I will see it later.
Yeah. Okay. So, are there any questions about this result? So, okay, using this technique, we can extend extend the technique to other situations. So our second result is that suppose we're given a graph that contains a half minus epsilon size independent set. So it's not 3 colorable or almost 2 colorable. We only guarantee that it has a large independent set. But here the expansion requirement is weaker. We only need that the spectral gap is at least some constant times epsilon. Then again, we can find a large independent set.
But the guarantee on the side of the independent set is better.
It's larger, yes. So instead of 1/3, it has half minus epsilon. Yes. Thank you. And we also, okay, so far these two results, our guarantee is that the graph has edge expansion. So the assumption is all about the spectral gap. We extend this result to some. Oh, sorry. As an immediate corollary, we also get an algorithm for almost 2 colorable graphs. It's just a very simple corollary. Yeah. So I was gonna say that we extend our result to, instead of edge expanders, we extend this to certified small set vertex expansion. So for now, I won't go into details of what this means, but I'll briefly touch on this towards the end when I talk about some open directions. This is very related to the graph decomposition that Siddhant mentioned. Okay, so these are our 3 results. Any question? Okay, so I guess now for the rest of the talk, I'll mention 2 of our main ideas. The first is an approximate packing theorem for large independent sets. What this means is we show that there cannot be too many near disjoint large independent sets. And I will define what near disjoint mean later. This can be equivalently viewed as an approximate covering problem. We show that if you have constantly many large independent sets, then they cannot be distinct. 2 of them must have some large overlap. I'll tell you precisely what this means later. Second idea is just a proof of almost uniqueness implies rounding algorithm. And this is done by rounding multiple samples from a pseudo distribution. And this idea has been done in some previous work on unique games, the problem of unique games. Okay, so these are the 2 high-level ideas that I'll try to describe for the rest of this talk. So let me start with expanders with half minus epsilon size independent set. And I'll talk about what the approximate packing of independent sets mean. So this is the theorem 2 instead of theorem 1, because this proof is a lot easier than theorem 1, so I'll present this first. Remember theorem 1 is for 3 colorable graphs, and theorem 2 is this case, where you have a large independent set. Okay. So let me start with a discussion on uniqueness of solutions. There has been a lot of progress on rounding sum of squares relaxations for average case problems. And in a lot of these papers, there's implicitly a meta principle, which states if you're able to prove that the solution is unique, then roughly there's an algorithm to find that solution. This is like a meta principle, a high-level idea. This has been extended to small list decoding. So if you can show that you have few distinct solutions, then there's an algorithm to find one of the solutions. And this principle has appeared implicitly in a lot of these average case problems, dictionary learning, tensor decomposition, robust statistics. And in fact, Pravesh has worked on many of these papers. So we can view our results as applying this meta principle for a worst case problem, which is the independent set problem. Okay, so uniqueness of solutions. So now we need to define what uniqueness of independent sets mean. How do we define distinct independent sets? Okay. So for 2 independent sets, x and y, represented as a 0, 1 vector, and suppose that they are large, they have size half minus epsilon. One should expect that they have intersection of roughly 1/4 size, 1/4 minus O of epsilon. And here's a picture. These 2 independent sets, they partition the graph into 4 clusters. For example, this cluster is a vertices with that where xu equals 0 and yu equals 1. Similarly, this cluster is xu and yu equals 1. Okay. And in particular, this cluster is the intersection between the 2 independent sets. So as you can see, if these independent sets are like kind of random, then these 4 will be roughly equal, and this set will have size roughly 1/4. Okay. So this motivates us to define the distinct independent sets to mean that they have intersection at most 1/4. Okay, so far so good. So here's our main packing lemma. We prove that if the graph has spectral cap at least constant times epsilon, then for any 3 independent sets of a large half minus epsilon size, 2 of them must have intersection larger than 1/4. Actually, in the proof that I'll show you later, we show that it's actually something close to half. In other words, this means that there cannot be three distinct large independent sets, where distinct means the intersection of size at most one row. Does this lemma make sense to everyone? Okay, I will. So this is the approximate packing property that we call. Basically, there can be not too many distinct independent sets. So let me show you the proof. The proof is quite simple. And by the way, this is a purely combinatorial property, and I'll talk about the algorithm later after I prove this lemma. Okay. First claim. Let's look at this picture. We claim that the 0,0 cluster has size at most the 1,1 cluster plus 2 epsilon. This is very simple. This is just
the edges in this graph are where edges can be.
Yes.
There are certain paths which cannot have edges.
Yes. Thank you very much. So think of these as clusters of vertices, and this one edge is like a lot of edges between clusters. And notice that you cannot have any edge between these two, because the second independent set, because these two form the second independent set, so there cannot be any edges in between. And actually, this is a tensor product of some two vertex graph. Yeah, thanks for that, Abi. Okay. Anyway, so I'll prove this claim in a few lines. First is using the fact that these two independent sets are large. So these two, 1, 0, and 1, 1, is the first independent set, and then 0, 1, and 1, 1 is the second independent set. They must both be at least 1/2 minus epsilon. When you sum them up, you get that 0, 1, 1, 0, and 2 times 1, 1 is at least 1 minus 2 epsilon. But we know that these four, they sum up to 1. So then you can just replace this 1 by the sum of the 4. You get this. W0, 0 minus 1, 1 is at most 2 epsilon. That's it. That's a proof. A very simple 2-line proof. Okay, so now we have shown claim 1. We need to use the expansion property of the graph. So there's a natural set that we can look at, which is this set, 0, 0, and 1, 1. We want to look at the expansion of this set. So how do we use the spectral graph of the graph? We know that, okay, well, this is a claim that we want to prove. And we look at the expansion of these two clusters. The outgoing edges of these two clusters are these two red edges, or like the edges between these clusters and these clusters. So the outgoing edges is at least the spectral gap times the size of the set times 1 minus the size of the set. This is just a usual notion of edge expansion. Okay, but now here we want to use the regularity of the graph. So we know that, first of all, by regularity, we know that the weight of a set of vertices equals the weight of the incident edges of this cluster. So 0, 0 is equal to the edges that is incident to. So it's this edge, this edge, this edge, and this edge. It's the sum of these four. But 1, 1 only has one incident edge, which is 0, 0, 1, 1. Okay? So when you subtract this by this subtract this is an upper bound on the left-hand side of this inequality. Whereas W0, 0 minus 1, 1 is the left-hand side here. This proves the second claim. Does this make sense to everyone?
What happens for irregular graph?
So sorry?
What happens if the graph is not regular?
Yeah, so if it's not regular, then now we need to look at what spectral gap means. So I guess in that case, you can look at the Markov chain. and the second the second eigenvalue of the Laplacian of that Markov chain. But then now you need to think of what the weights of vertices mean. So
No, but the bottom line is, do you have an argument also for without assuming regularity or not?
no. So for this we need regularity.
Approximate
but-
regularity is
Probably,
fine.
yeah, that is probably fine.
So if all the degrees are within the fixed constant factors of each other, that would be okay.
Yeah. And okay, by the way, the third theorem that we have, which is small set vertex expander, that doesn't need regularity, and I'll briefly talk about that in the end. Like, it's crucial for the recursion for it to work. Yeah, that will be I'll talk about that in the end. So, but this proof makes sense. It's pretty short, pretty simple. So now we want to combine these two claims. So combining these two, we get that the weight of 0, 0, 0, 1, 1 times 1 minus 0, 0, 1, 1 is at most 2 epsilon divided by lambda, which is by moving lambda to the right-hand side. So if lambda is a large constant times epsilon, we get that this is at most 0.1. So think of lambda is like 100 times epsilon. And you get this.
This says that 1% of the edges go between 0, 0, and 1, 1. It's most.
Sorry, this is the
It's the
this is
weight.
actually the sum of. Okay, sorry, the notation is a bit off here.
So what's the meaning of this?
This meaning is the weight of 0, 0, 0 plus the weight of 1, 1.
Fraction of vertices labeled 0, 0 and 1, 1.
Ah,
Yeah, yeah.
I'm a bit confused.
Sorry about this. The
It's
notation
just the
here.
set side.
Yes, it's the same set
Set
size.
side. E denotes edges,
E.
but yeah, okay.
Yeah,
But
yeah. Sorry, I should have mentioned this. Here, E denotes the weight of the edges across clusters, and W just means the size of the clusters. So yeah, so 0, 0, and 1, 1 means the sum of these two clusters. Yeah, thanks for the clarification. Okay, so but what does this mean? This means that either this has to be very small or it has to be very large, right? Because this is a quadratic inequality. So there are two cases. Either it looks like this, where 0, 0, and 1, 1 is very small, or 0, 0, and 1, 1 is very large. Now notice that in the second case, we are done, because 1, 1 is the intersection between the two independent sets. And we showed that this is roughly, this is 0.9. So then 1, 1 is like roughly 0.4045, which is much larger than 1/4. We only want it to be larger than 1/4. Okay, so the second case we're already done. The first case, what do we do? These are very small. So now this is a point in time that we look at 3 independent sets. Remember, this is just a statement about the intersection between 2 independent sets. Now we look at 3 independent sets. And suppose for each pair, we're in the first case, that this sum is at most 0.1. Well, this cannot happen. Let's see. So suppose we look at the first 2 pairs of independent sets, and then 0, 0, and 1, 1 needs to be at most 0.1.
So you have 3 coordinates, one for each independent.
Yes.
This star means you don't care about this one.
Yes, star means that if you ignore the third one. So if you look at the first 2, you have this inequality. You look at 1 and 3, so ignoring the second one. Same thing. Same thing for second and third. Okay, well, now you just sum them up. On the right-hand side, you get 0.3. On the left-hand side, I claim that this covers everything. So it must be larger than 1, at least 1. Why is that? Because if you have a string, length 3 string of 0, 1 vectors, it must have either 2 zeros and 2 ones. So this covers everything. So then we get that 1 is at most 0.3, and this is a contradiction. So because there's a contradiction, it means that one of the pairs of independent sets must be in the second case. Must have that 0, 0, and 1, 1 is large, which means 1, 1 is larger than 1, 4. That's the end of the proof. Any questions?
Can't you get the two pairs actually have this one?
Just two.
Well, you got one pair that satisfies, that's phased.
Ah,
The
good
gap is
question.
really large here, so can you get the two of the three have this property?
Ah, that's a good question. I think I might be able to construct a counterexample.
Like if you take two color classes, two of them are this color class and one of them is this color class, you only get one pair that is overlapping, right?
Right.
Yeah, so you can maybe have a situation where only one of these inequalities is violated, but the other two are in fact satisfied.
If it's violated, yeah, okay.
Yeah, thanks so much, and thanks, Hans. Okay, so this is a proof of the combinatorial packing property of independent sets. Hope it's like simple enough that everyone can understand. And then I'll tell you a bit about why we need the intersection to be larger than 1/4. So this is the algorithm part. Why does this imply that we can efficiently find an independent set? So I'll just give you the high level proof. Suppose you're given a distribution over independent sets. So it's a distribution over 0, 1 vectors.
Independent set of size half-line sub-zero.
Yes, so we actually don't need that. We only need that this is satisfied. But the proof of this requires that they're large, yes. The argument here doesn't need the size condition on the independent set. Okay, so let's parse this. So let's consider the product distribution. And we sample two independent sets from this mu independent. So let's write out what W11 means. W11 just means that the fraction of vertices such that XU and YU are both 1. So this is just rewriting W11. But then you can swap the expectation and write this as fraction of expectation over vertices, P squared, PU squared, where PU is defined to be the expectation of X sample from mu, XU. Good. So this is just some trivial rewriting of the equation. So now we know that this quantity is at least 1/4 plus some small constant. So just by a simple Markov inequality, we know that at least omega delta fraction of the vertices have PU larger than half. Yeah, like if the expectation is larger than 1/4 plus delta, then we know that delta fraction of this has this quantity larger than 1/4 plus delta, which means PU is larger than square root of 1/4 plus delta. Make sense? Now I claim that these vertices form an independent set. So why is this the case? Let's just consider two vertices. Suppose the marginal distribution on these two is more than half. So for each vertex, there's a probability more than half that it is contained in the independent set. Then this means that there's a non-zero probability that both of them are in the independent set, right? That means there cannot have there cannot be an edge between the two vertices. Okay, so then we're done. There we have this is an independent set, and it is a delta fraction, constant fraction. Yes, that's it. That's the algorithm. And of course, I'm hiding a lot of things. Like we don't really have a distribution. We only have pseudo distributions. And I guess for people familiar with sum of squares, pseudo distribution basically behaves like a distribution, but we only get access to the low degree moments. But everything here is still fine because these are low degree moments. And we don't really have this as well. We have this squared. So there's some things we need to do. But this is roughly the high level idea.
What do you have square?
So we have that instead of this, we have the expectation over xy, w11 squared is larger than like 1/16.
Because you have the quadratic.
So we need to do some, there's some extra work to do. Basically, we need to do some, for people who know, there's this global correlation rounding technique that reduces pairwise correlation. Yeah, so-
Integrate for sum of squares or something like this.
So there we need some large constant degree
Large
sum of
constant.
squares. Yes. If that didn't make sense to you, don't worry about it. It's just that is some standard technique that like by now it's pretty standard for people who work on sum of squares. Okay. So that's it. That's the combinatorial lemma and the algorithm for large independent sets. Any question?
Yeah, you said that it was using some uniqueness of solution. Why do we see it here?
Because we define distinct solutions, distinct independent sets, to be if they have intersections smaller than 1/4. So I guess maybe let me.
This implies that taking this high probability vertices is like a solution.
Yeah, so maybe I can interject a little bit.
Oh, yes.
So, you're saying imagine any distribution over large independent sets of the graph. Then what Tim just wrote on the slide following this is that, if you take two samples from this distribution, these are like just two independent samples, then, their intersection must be large. So if like two independent samples of the distribution has a large intersection, this can only happen because all of the samples, somehow are correlated. So that's basically saying that, every independent set in the distribution support must be somehow like non-trivially correlated with like some, maybe like a pair of possible independent sets.
Right, I guess it's the one when which the marginals are higher than half.
Exactly.
This
And so then the other.
particular one is the independent.
Exactly.
Yes. Thank you. Okay, so I guess I'm done with the independent sets, and I'll move on to three colorable graphs. Okay, let me go back to that slide. Okay, so now I'll talk about three colorable expanders and what does approximate packing of colorings mean. Okay, so now let's look at let's think about what the agreements between two colorings mean. So can people tell me, are these two colorings, this is a triangle and there are two colorings here. Are they the same coloring? Yeah, they are the same coloring, right? Because you can permute the color classes. Yeah, so even though these are different, but you can permute the colors and they should be the same. So so we want to define the agreement between colorings in terms of a permutation over the three color classes. Okay, so agreement of x and y according to pi is a fraction of vertices such that xi equals pi of yi. Okay? And then the agreement between x and y is just the maximum over the permutation. Sounds good? So here's an example. These two colorings, so they're not up to isomorphism. These two colorings have agreement half, because on the left-hand side, you can only match one of them. On the right-hand side, you can only match one of them. So yeah, so this is an example of where agreement is half. Okay. And now let's look at two colorings, and it partitions into 9 clusters. And the graph looks like this. And this graph is just a triangle tensor 2 graph. And similar to the previous case, like this cluster is like the vertices where both colors labeled as 1. Okay. And remember, we are interested in the agreement between two colorings according to some permutation. And that corresponds to the triangles in this graph. So each of these permutation correspond to a triangle. So for example, this green one is an identity permutation, like 1 maps to 1, 2 to 2, 3 to 3. And then this red one is 1 to 2, 2 to 3, 3 to 1. So if we say that agreement is small, it means that all of these triangles are small. And so one can expect that if these two colorings are like kind of random, then the agreement will be roughly 1/3. Okay, so this motivates us to define the agreement. But we actually need agreement to be slightly larger. But we define distinct colorings to be agreement at most half. So not just 1/3, but we need half. And later I'll show you why we need half. Pretty much the same as the previous case. So now here's our main combinatorial coloring packing result. If the spectral gap is at least 1 minus some small constant, then any 3 colorings must have, so for 2 of them must have large agreement. And here we need this extra condition that no color class has size half. Because if one of the color class has size half, then we are already done. We can find a large independent set. Well, suppose this is true, then 2 of them must be have large agreement. This, in other words, there cannot be 3 distinct 3 color. Very distinct is defined as agreement at most half. Okay. So I'll tell you the proof. The first claim is that if this is for 2 colors, if they have small agreement and if the graph has expansion, then the graph is almost bipartite. Let's see the proof. So just as a reminder, we define, so the agreement are these triangles. So we define S pi. Pi is a permutation to be I and pi I. So and then the agreement of xy according to pi is just the weight of S pi, like these triangles here.
There should be 6 triangles.
There should be 6 exactly. I'm highlighting 3 of them. Yes. Yeah, I'll show you right here. Yes. So notice that this 9 vertex graph is partitioned into 2 triangles. So this is this highlighted here is one specific partition. And if you look at it closely, you see that these 3 correspond to permutations of the same sign or same parity. So there's another partition, like this triangle here, and it's not highlighted here, which correspond to the negative permutation. Yeah, permutation of the same sign. So there's 6 different permutations, and there are 2 different partitions of this 9 vertex graph. That makes sense to everyone? Okay, so now we want to use the expansion property. And we're going to apply the spectral gap to each of this triangle. So we know that the edges between a triangle and its complement is at least the spectral gap times the size times 1 minus the size of that triangle. Now the obvious thing to do is to sum up all these inequalities over the 6th permutation. So on the left-hand side, I claim that this is 1. And we can kind of just stare at this graph and prove this, but one way to see this is that each edge is contained in exactly 1 triangle. So yeah, this is not too hard. On the right-hand side, the sum of WS pi is 2, because we have 6 triangles and 3 of them partition the graph. And then now this term is just the sum of the WS pi squared. Rearranging, we get sum of WS pi squared is at least 2 minus 1 over lambda. So when lambda is at close to 1, then this is also close to 1. Okay, this makes sense to everyone. It's just summing up this inequality. So now what do we know? We have 6 triangles. So think of this as 6 variables. so for these variables, they sum up, three of them must sum up to 1. And then we know that their sum of squared is at least 1 minus epsilon. Okay, so basically these are equalities and inequalities that that are applied to the 9 vertex graph here. Okay, so how can one example that this can occur is this. So there are 6 triangles, 4 of them is half. These 3 sum up to 1, these 3 sum up to 1. And their sum of squared is at least 1 minus, is exactly 1. This is one example.
The six triangles or 6 partitions?
These are the 6 triangles, the size of the 6 triangles. So there are some overlaps between the triangles. But if we write the weight of the triangles out, there are 6 of them, and these are the weight of them. And remember that each triangle corresponds to the agreement between the 2 colorings, according to some permutation. So we know that, okay, so either one of the agreement is larger than half plus some small constant, or if this is not the case, if all of these numbers need to be smaller than half plus delta, then we know that, or we can prove that 2 of them must be close to 0. Basically, this example is the only case. So two of the triangles must be close to 0. This basically means that you can like kind of delete 2 triangles in here. What does this give you? This gives you something that looks like a bipartite graph. Let's say we delete the triangle 1, 1, 2, 2, 3, 3. Also 1, 1, 2, 3, and 3, 2. Let's delete these 2 triangles. Now we are left with this 4 vertices. 1, 2, 1, 3, 2, 1, 3, 1. And they form a bipartite graph. The graph is almost bipartite. So does this make sense to make sense? Any questions? We showed that, so we've seen that we need small agreement between the 2 colorings and strong edge expansion. If these 2 imply the graph looks like these. Like these 5 are very, very small. These 5 clusters are very small. And now the question is, what do we do next, right? So similar to the independent set thing, we now, instead of 2 colorings, we look at 3 colorings. And so now 3 colorings, there are 27 partitions. I won't show you a graph of it because it's going to be messed. But basically, just by some simple case analysis, the graph will kind of look like this. This is an example, but it will pretty much look like this, plus some small thing that I didn't draw out.
This accounts for most of the vertices.
Yes. So this 4 will have like weights 1 minus O of epsilon. Yeah. So I don't think I have time to go into the details here, but the conclusion here is that either a color class is larger than half, in which case we are already done, or if it's not the case, then we must have that 2 of them has agreement larger than half. So yeah, I only have 7 minutes left. So let me not explain this. But that finishes the proof of the packing property of 3 coloring.
But the same averaging argument that this result is a similar averaging argument as in the independent case.
Yeah, it is similar. It needs to do some case analysis, but it's not too hard. Yeah. And I'm going to show you why s pi larger than half gives an algorithm. It's actually almost the same idea as the previous case, where and okay, because I don't have much time.
That's okay. You can go a little bit over.
Oh, okay. So it's actually almost identical to the previous case, but you just write W of s pi out. So W s pi is the fraction of vertices with x2 equals yu, and here because we assume pi is identity, so this is the definition of s pi. Then because x and y are sample independently from mu. This, before that, you can write this as sum over the color classes of xu and equals yu equals sigma. This is basically just expanding these out. And now, because x and y are independent, you can write this as a square. So we know that in expectation, the sum of probability squared over the three color classes, this is equal to S5, right? And now we just upper bound this by this quantity, because the sum of probability x3 equals sigma without the square must equal 1. Each vertex must get one color. So this is upper bounded by 1 times the maximum of the 3. Okay. And we know that in expectation, this quantity is at least half plus delta. Again, by Markov's, at least delta fraction have this quantity larger than 1/2. Okay, basically, delta fraction vertices have that one of the color classes satisfy probability of x3 equals sigma, larger than 1/2. Well, but this means that delta over 3 fraction, also there is a sigma such that delta over 3 fraction of vertices satisfy this. And again, it's easy to see that this forms an independent set. Any questions? Okay, and just want to mention again, I'm adding a lot of details in here, but that's the main idea. So I want to end the talk with an open question or an open direction, which is for arbitrary graphs, but with a large half minus epsilon size independent set. So this is the harness harness and Besson algorithm that I mentioned earlier in the talk. We know half minus epsilon versus epsilon is usually hard, and this is the best we know in this setting. So if epsilon is the 1 over root log n, we know something better. But if epsilon is a constant, this is really the best known algorithm for 20 years. So clearly, we can ask if the graph contains a half minus epsilon size set, can we find one of size n to the negative epsilon? This is not ruled out by any harness assumption. So okay, given our algorithm for finding independent sets on expanders, well, the natural thing to do is to do graph decomposition. So in a lot of works, like for example, the famous work by Aurora, Barag, and Stoyer on unique games, sub-exponential time algorithm for unique games, they first decompose the graph into pieces of small threshold rank, and they're able to small threshold rank basically just means like kind of expanding, small set expanding. So they're able to decompose them into pieces, solve each piece. Okay. What about the independent set problem? Can we do that? Now the question is, once we decompose it into pieces, and then we solve it within each piece and find some large independent set, how do we piece them together? So it turns out that a lot of graph decomposition algorithms that exist, that have been used, they focus on only removing a small fraction of edges. But this won't work for our independent set problem because we don't know how to piece them back together. But this suggests a natural avenue or natural direction, which is vertex expander decomposition. Let's see, suppose we find a non-vertex expanding subset. So we know that this subset has few neighbors. Then what can we do? We can just remove these neighbors and then recurse on these two pieces. So because these two pieces because we have removed the neighbors, these two pieces have no edges crossing. Then if we recurse on these, we can just output the union of these independent sets. So that's one natural way to do the graph decomposition on arbitrary graphs. And let me restate our third result. So given a graph with size half minus epsilon independent set, and that has a certificate of small set vertex expansion, then we're able to find a size independent set of size constant. So what does this mean? So in the previous two results, the edge expansion case, by Cheeger's inequality, the spectral gap immediately gives you a certificate that the graph is an edge expansion, an edge expander. But for vertex expander, we don't really have that strong Cheeger's inequality. We have something slightly weaker, but that loses a log degree. So when the degree is somewhat large, then we don't get anything. So well, obviously the question is, can we decompose our graph into a certified small set vertex expander? So either we improve this, like maybe perhaps remove the certificate, or we do some decomposition with a stronger guarantee that each of them is a certified vertex small set vertex expander. So that's the one. This is really the reason why we study vertex expander in the first place. In the hope that we get a decomposition algorithm and like which works for arbitrary graphs. So that's it. That's the end of my talk. Thank you.
Do you think it should be possible to remove the assumption that the graph is regular, or almost regular, in all the theorems?
Okay, so this theorem doesn't need, because vertex expansion doesn't really need regularity at all. It's just some combinatorial property. But for a spectral gap, you kind of need to first define a Markov chain, and then that is not. It's not clear whether you can remove the regularity assumption. So you can define the weight of vertices to be according to the stationary distribution. But yeah, there we don't know.
Can I say something?
Yes.
So I think it's likely that you can get a rounding into 1 over log n size independent sets. And the idea is simple, like somehow, you would want to bucket the vertices according to the weight they have in the stationary distribution, and then select the largest bucket. And now in some sense, sort of approximate regularity for free. It requires work, but I think, and we did not, work this out completely, but I think if you don't have any regularity, then we won't immediately get a strong enough result of the sort Tim presented, like linear size rounding, but 1 over log n should be plausible.
So suppose you weaken demand to producing only an almost independent set, namely a set with very few edges.
Oh.
I wonder first of all whether the hardness does that work. And on the other hand, it seems that with edge expansion you can get this.
Yes.
The decomposition to edge expander. So maybe you can get this, and I wonder whether the hardness is that work.
Yeah, this is a great question. And basically, Avi is getting at the fact that when you have these decompositions into small set expanders, you only remove a small fraction of edges. So if you now turn your problem into a non-strict CSP, then you should be able to do similar to what. Yeah, it's a good question. I don't think we thought too much about this.
More questions.
But the hardness result that's a
More-
harder problem. No, it's an easier. Oh, I see.
Yeah, no, if you allow, it's not clear that the hardness results is that. But they show that if you have half minus epsilon, it's hard to find an epsilon fraction independent set. But maybe it's not so hard to find almost.
But
If you have an almost independent set, for the right definition of almost, you can kind of turn it into a real independent set, right?
Yeah, but
Well, but it would probably have, the number of edges will not be sublinear, of course.
exactly.
Yeah, it will be superlinear.
No. If the vertices are constant degree already.
I know, of course, that's obvious. So it will probably, you have to allow, I don't know, degree polynomial.
So we are in a
It's
dense
very,
averaging.
very sparse. You start with a very dense graph, right?
Oh,
This
okay.
input graph is the degree root, and you will return a graph of degree log.
Yeah, but it's a good question.
And maybe the hardness result works, so then it will be very interesting.
I would suspect not, but yeah, I guess
Yeah.
Okay. All right, great, yeah.
I was like, okay, something. For this, like, is there some? I remember earlier you mentioned that there's some hardness against finding like large independent sets in graphs that have size independent sets of size 1/2 minus epsilon. So like, does that mean that you shouldn't be able to find vertex expansions that are like too good or something? Like vertex.
Oh yeah, so yeah, exactly. So this is constant size is ruled out for arbitrary graphs. So yeah, I think it's written here. Yeah, this one. But so clearly you need to lose something. Either in the decomposition or maybe you only get a n to the epsilon size thing that you can work with, for example.
Or the unique game conjecture is false, which is possible.
As far as we know, that's not ruled out. Yeah.
Okay, thanks.
Yeah, thank you very much.